So this is a 1 week GAN program on spectral graph theory. We have our expert Professor Sebastian Schioba from University of Delaware. First, I will briefly tell about his profile, and then we will move on to the lectures. Okay. So he did his bachelor's from University of Bucharest, Romania, and then he did his master's and PhD from Queen's University at Kingston, Ontario, Canada. And then he was a postdoc at University of California, Santiago, with Fan Chung, and then he did his postdoc in University of Toronto in Canada. Then in 2009 he joined in the University of Delaware. So right now he's a professor in the Department of Mathematical Sciences in University of Delaware. Yeah, with this brief introduction, I request Mr. B to start.
Okay. So I have to go in the camera. Yeah. Yeah, that's okay. So thank you for the introduction. I'm very honored and very happy to be here in India, in Hyderabad. This is the first time I've been in this country, and I've had a wonderful time thus far. So today, I don't know much about your background, and so we'll have a course for 1 week on spectral graph theory. I'll try to set up the foundations in the first lecture today, and we'll progress to applications and to interesting problems throughout the week. So the first day may be a little bit known to some of you because we'll go over some basic stuff in linear algebra and some basic stuff in graph theory. But hopefully you'll find something interesting in what we discuss today. Okay, so let me get my stuff from here. Okay, so I'll write something here. I'm going to use the blackboard for most of the talk, but this is a fancy screen, so I don't get to use it that much. So why not? We used it yesterday. But now, hopefully I remember how to do these things. Let's see. Okay, so the course is about spectral graph theory. So what is spectral graph theory? Well, you have in mathematics you have many areas. So one of them will be graph theory. Combinatorics and all that, discrete structures. And you have, on the other side, you have linear algebra, where you have matrices, eigenvalues, eigenvectors, and all that. So spectral graph theory, what it does, it studies the connections between these two areas. So maybe when you're young and you're undergraduate, I know that it happens to some students that I've taught, you believe that mathematics is a bunch of separate islands that don't talk to each other and so on. Well, you know, hopefully by now, the more you learn about mathematics, you realize that many things connect to each other. And so it's not a surprise here that you have a rich interaction between graph theory and discrete structures, like I mentioned, and linear algebra. So in this type of problems, you can, if you have a graph, you know something about its structure, something of its properties, the question will be how does that reflect in terms of linear algebra properties, and vice versa. If you know something about the linear algebraic properties of the graph, how does it reflect in terms of the structure? So in this course, I will give you examples where these things happen, and there are many situations in which linear algebra provides a solution to like graph theoretic problem, combinatorics problem that we wouldn't be able to get in any other way. So it's an interesting area. There's okay, so that's the key principle about the course that I'll try to convince you this week. Now I will start. Do we have chalk? No, sorry. Okay, so today, like I said, we'll talk about linear algebra. And I have a colleague at University of Delaware who told me once that you can never know enough linear algebra. So whatever you think you know about linear algebra, maybe there's more to learn. Like I said, some of these things maybe you already know, but I want to start here just to kind of lay a foundation about what we're going to talk for the rest of the week. And the key idea here, or tool in spectral graph theory is the spectral decomposition theorem. And because I will talk about undirected graphs, the matrices that we'll talk about in this this week will be real and symmetric. So this is what we'll talk about. So this is the key thing. Everything that will derive, like the results that we'll discuss this week, they will come from, like, at the bottom of it, everything is from spectral decomposition theorem, and we'll talk about it in a second. I'll tell you a little bit about it. And that explains, for example, maybe some of you are more advanced in this area, and maybe you have looked into, you know, how do you so let me put here some star. You know, how does one study spectral, maybe hypergraph theory, or spectral directed graph theory. These are just names that I made up right now. So you see, like, in attempting to generalize the results from spectral graph theory to other realms, like hypergraph theory, where edges have more than just two vertices, or directed graphs, where just because you have something from x to y doesn't mean that you have something from y to x. This is the main block that one has to overcome, and also that's the approach that people have taken in some situations. Maybe I'll talk about it towards the end of the class. But for example, if you think about spectral directed graph theory, like if you have directed graphs, the matrices that, if you associate matrices to these directed graphs in the way similar to the way you would associate adjacency matrices, those matrices are not going to be symmetric. And so that puts a stop very quickly into anything that you try to develop. And that's why in this area, people have looked at something more general than real and symmetric, which are called Hermitian matrices. So that's why today, when I will tell you about the real and symmetric matrices, I will give you I'll give you two ways of looking at it. One, I will give you a proof of the spectral decomposition theorem, which is just for the case of real and symmetric matrices. And then I'll put that into a more general context. There are several spectral decomposition theorems in linear algebra for something called Hermitian matrices, or for normal matrices. And those are the approaches that people have taken when trying to extend some of the work from spectral graph theory to these new realms. Okay, so this is just some introductory stuff, just to kind of set up the main ideas. Okay. So like I said, we're going to start at the beginning. So definition. So for me, let A be so we'll have a matrix, and I will denote here. You can have M and C, which are the set of all n by n matrices with entry complex, or for now, let's do it like this. And you can be also over real. This is something that everybody knows. We say that lambda and u form an eigenpair for A if what has to happen? Well, lambda is a complex number, u is a vector which is not zero, and you have this equality that everybody knows. Okay, so that is what is an eigenpair, and in this case, lambda is an eigenvalue, and u is an eigenvector. Corresponding eigenvector of A corresponding or associated to lambda. Okay. Now, so eigenvalues, eigenvectors, I'm not going to go into a discussion. If you want to know like the deeper meanings of things, these days everybody is looking quickly for conceptual meaning or things like that. You can look into, go on YouTube, but not now, later. And there are many like videos. 3 Blue, 1 Brown has very nice videos about the meaning of eigenvalue and eigenvector, and so on. So, okay. Now, again, in spectral graph theory, we're going to have graphs, we're going to have matrices. Matrices are going to have eigenvalues, eigenvectors, and we're going to try to study them this week. Okay, so this is basic stuff. Now, the first proposition is that every complex matrix has an eigenvalue. But let's do something else instead of, so I'll show you a proof that is from, I guess I forgot to give you the resources. So I'll put here some books for the things that I'll talk today. Now, in linear algebra, like I said, there are many facts and sometimes you forget things. The book that I use to kind of, if I want to recall or if I want to find anything about matrices, is a book by Roger Horn and Charlie Johnson, which is called Matrix Analysis. So most of the proofs that I'll give you today in terms of linear algebra are taken from there. So I highly recommend it. It has a lot more than I'm showing you here. And you don't have to learn the whole linear algebra before you go do spectral graph theory, but it's useful for you to know some important spectral linear algebra before you do anything. Okay, so actually, let me give you the statement 2, the more general statement that will imply 1. So I wrote it here. For every vector which is non-zero, there is a polynomial g of x, again, let's say over complex, of degree. Okay, let me put here, before let A be, I have my matrix here. So for every vector non-zero, there is a polynomial g of x of degree n minus 1 or less, such that GA times V is an eigenvector. Okay. So obviously, if you know 2, you know 1. So we'll just go quickly over 2. So we have V. Let's pick V not 0. And you've probably seen this argument before. It's a dimension argument, and that's how we do most things in linear algebra. So I'll write here on the side. If you have this this V, you can look at V, you can look at AV, you can look at AN over V. So here you will have n plus 1 vectors, but they all live in an n-dimensional space, so they must be linearly independent. So there is a linear combination of them that gives you 0. Okay, and you can be a bit more clever about it, and you can say define M to be the least K such that V, AV, AKV are linearly dependent. So clearly, such a k exists because n satisfy, but maybe you got lucky and you can, you know, like there's a smaller exponent, so you can just take the smallest one of them. So now you basically just work out what that means. Okay, what does it mean they're linearly dependent? Therefore, there are some constants, let's say, did I put them here? Okay. A0, AM complex, not all zero, such that A0 V plus A1 AV plus AM AMV, it gives you the zero vector. Okay, and then you're almost done. So if you haven't finished copying and so on, and you want me to leave something on the board, just say something. Otherwise, I'm going to go ahead and just erase the board. So, yeah. Okay. So then you can define P of x to be this A0 plus A1x plus AMXM, and then from there we have that PA if it equals 0. Okay? And now you have to use something, and so what you have to use is this fact about polynomials with complex entries, that they have some kind of, they have complex root. So then you can take that lambda be a root of P of x. So lambda is complex. So then what we have then, P of x is x minus lambda times g of x. And then you go from here, you go here, and you write what it means. So you can say this is 1, this is 2. What do you get? We get that a minus lambda I, this is n, ga of v equals 0. Okay. Do you see? So I factor P of x here is a like non-determinant or a variable, x minus lambda g of x. If I factor the polynomial of the applied to the matrix, is going to be, instead of x minus lambda, you have a minus lambda identity, and then the g of x gets replaced by g of a. Okay. So this looks very much, I mean, here we didn't quite say it, but you've probably seen it before. AU equals lambda u, it's the same thing as a minus lambda identity is 0, which is the same thing as the kernel of a minus lambda I is not trivial. You have something that is not just 0 in there. You have more than 0. And now here you have a minus lambda I times something is 0. So here's the first I'll give you help, call it trick question of the day. Does this mean that GA of V is an eigenvector?
No, so that has to be non-zero.
That has to be non-zero, very good. And that's where, you know, in order to say that this is an eigenvector, which kind of I wanted to, that's the conclusion, so you kind of guess that that's what's going to happen. You have to argue that GA of V is non-zero. And GA of V, G, like what degree is G? M minus 1. And we agree that that's why this thing helped you at the beginning, that you take M to be the least K such that these are linearly independent. Essentially, this is the least degree of a polynomial, or if you calculate P of A and you multiply by V, you're going to get 0. And so here, this G of A has degree smaller, so you can say by the minimality of M, by the definition of M, the fact that it's the smallest such that, we get that GA of V is not the zero vector. And now that's the conclusion, therefore, GA of V is an eigenvector of A. Okay? So, yeah, it's just a little bit different, so it's helpful to get used to kind of, you know, maybe undergraduates, whenever they see something about eigenvalues, okay, let's fire up the determinant and do characteristic polynomial. We'll do that, and you will see results about that, but you can do things without that. It's just a matter of like linearly dependence. Yes, question? Yes.
So here you're taking lambda to be a root of p of x, right?
Yes.
Yeah, we don't actually know what p of x is. So you're assuming there's a root of that polynomial.
Yeah, because so that's what I said, that here I'm using this big thing about p of x being a polynomial of complex coefficients, and hidden in the background, we're not gonna go all the way there. Yeah. So it's self-contained up to a point, like yeah. So you're absolutely right. So, yeah. Any other questions? No? Okay. All right. So yeah, this is important, and yeah, we'll use it for various things. Let me erase here. Now, poor organization on my part. I just erased the result that I was going to ask you about it. So here I did something for every complex matrix has some eigenvector. Is it going to be true for any real matrix?
It depends on the base field you're asking. So if you want a real eigenvalue.
Yeah. That's the thing. That's a very good question. So if I look at the it depends on if I'm looking at real matrix. Am I looking for so the first thing, if I'm looking for real or complex eigenvalues, or if I'm looking for real and complex eigenvectors? Okay, so that's the question. Okay, so I have done this, done this. Okay, so I'll leave you with this as an exercise for afternoon. Again, you can probably solve it in your sleep or something, but it's good to do it. So let A. So now the description of the real matrices that I asked a bit earlier. Assume that lambda u is an eigenpair of A, where lambda is complex number and u is also, I mean, I shouldn't write this, it's in the definition, but okay, so you have an eigenpair for, so A is real, you have an eigenpair lambda u, both of them are complex. How do you get yourself a real eigenvector? So if u equals, let me use this real part of u plus I imaginary part of u, then show that A times the real part of u, I'll talk about real part of u in a second, equals lambda times real part of u, and okay. So here you're going to have some complex entries, A1 plus IB1, AN plus IBN. So then you break it down the way you would do it for complex numbers, A1, AN plus I times B1, Bn. So this is the real part of U. This is the imaginary part of U. Okay? So this is exercise, so I'm not going to solve it because exercises are meant to be solved by who? Okay, by students. So this is the first part. And second part, at least one. Well, so let me just add here, sorry. Real part of U and imaginary part of U. The key thing about them is that they're real vectors. And then in order, again, the same thing before, just because A times something equals lambda times something doesn't mean it's an eigenvector. You have to check it's non-zero. But this is what you will do. At least one of real of U and im of U is non-zero. Okay. You've probably done this in some undergraduate class, but yeah, it's good for you to do it. Okay, so that's exercise 1, so we can keep track of them. And then exercise 1 comes exercise 2. Again, we can talk about this in the afternoon. You guys have questions? Yeah, it's okay. Okay, so now, okay, so okay. So from over there, you kind of know where we're going. Okay, I want to, for a real matrix, I can say something about my my vectors being eigenvectors being real. What do I want to tell you now? Okay, so let's do here if A is symmetric and lambda U is an eigenpair of A with, again, lambda complex and U real, I can then see if you can, is it true that lambda is real? Okay. Okay, so this is, again, these are like at let me erase here. These results form the foundation for the proof of what we're gonna do next. So I'll give you the I'll give you first the spectral decomposition theorem for real and symmetric matrices, because this is the only thing we'll need for this is the only thing we'll need for this week. And after we go through this proof, I'll give you another perspective of it, which is broader, which gives you, in which this theorem is a consequence of a bigger theorem called Schur's theorem, which this Schur's theorem is not something super complicated. But the Schur's theorem allows you to, with one stone, you can kill like many birds. So Schur's theorem is going to be a general theorem, and its consequences are going to be the spectral decomposition theorem for Hermitian, for real and symmetric, for normal matrices. So if but I think it's important for you to know both of these kind of approaches. And so let me state this for real and spectral, and sketch the proof. So let A be a matrix here, A symmetric. Then, okay, what do I want to say? What's the spectral decomposition theorem? Well, you can phrase it in different ways. So let me give you two different ways. Then one way that is going to be useful, this is one way that will apply it in many situations. Rn has an orthonormal basis formed by eigenvectors of A. So again, at the beginning you may say, okay, what's the big deal? Well, the big deal is everything in this space is going to be written as a linear combination of eigenvectors of A. So everything in this space, I mean, the space is large. There are many things. There are many things that are not going to interest you. But everything that is going to interest you that is a vector will be a linear combination by eigenvectors of A. So you can relate it to A. So that's going to be very important. And then if you take this orthonormal basis and you look at these vectors, because we look at the vectors usually as column vectors, and you put them in a matrix that is a column matrix, what you'll get is so this will be equivalent. There is a real and orthogonal matrix U. So orthogonal just means that U transpose U equals the, so the columns are form an orthonormal system, such that A equals, how did I write it here? AU, just one second. You can write U transpose AU equals D, where D is a diagonal matrix, where U transpose AU, or you can write it the other way if you want. Okay, so okay, so let's go through a quick proof of this, and then we can look at the extension also this morning. Okay, so the proof will go in a sequence of steps. Some steps will prove, some steps will leave it to you, some steps you know, so we'll go like that. What is the first part? The first part we already seen that, so we have let A be here. The first part is that the matrix A has a real, let's say, eigenpair lambda U, so lambda real U real. So based on what we mentioned earlier, you start with, okay, your matrix is going to have one real eigenvalue, one real eigenvector. And then we're going to do something to it and get so what we want to do is we want to get an orthonormal basis formed by the eigenvectors. That's what we're going to do. Okay. And here's the general procedure that, again, is very useful for you to know. If we have A, if you think about if you have an eigenvalue and you collect all the eigenvectors that correspond to that eigenvalue, together they form an eigenspace. And what's a consequence of that being an eigenspace? The consequence is if you take a vector from the eigenspace and you multiply by A, you stay in that eigenspace. The eigenvectors are even more special because if you take an eigenvector, you know exactly, you just scale the eigenvector and you multiply by adjacency matrix. Now, so in general, we have this notion. So let's say, let U be, I'll use this notation, be a subspace of Rn. We say that U is A invariant if U is contained, whenever you have a vector and you multiply it by A, you're not leaving the subspace. Okay, so that's a, so eigenspaces are going to be, you know, A invariant, but maybe they, you know, there could be more general things. So what's the result that we're going to prove here is that so A is real and symmetric if U is A invariant, then U perp, so this U perp is the collection of all vectors that are perpendicular to everything in U, is also A invariant. Proof 7. Okay, exercise 3. So in some situations when I put I get carried away with exercises, you can raise your hand and say, hey, can you prove it for us? But you know, so don't be shy about that. So okay. Okay, but here's the thing that we'll use. So you have 1, 2, you have now 3. If U is in Rn is A invariant, then, like I said, U could be many things, but what you will guarantee for sure is that U contains an eigenvector of A. So this one, maybe you've seen it, maybe you've not. I'm not going to leave this as an exercise, so we'll prove it right now. So, okay, so assume that U is an A invariant subspace of Rn. Okay, and let's say again, it's all about dimensions here. Denote K to be the dimension of U. Obviously, is at most n. Okay. So what we'll do, so this is a proof, you can find this proof in, so let me put another reference here. So another book, Chris Gottsill and Gordon Royal. algebraic graph theory. Okay. So now what we'll take a basis for U, and we're going to put those vectors in a matrix. So let R be n times k matrix. So this is what I call tall matrix. So here you're going to have C1, C2, Ck columns. So it's a matrix whose columns form an orthonormal basis for U. Okay, so it's a base. And now what we'll do is we'll write down what it means that U is invariant in terms of this this matrix. Okay, so first let's write it a bit informally. You have A times R. So this is R. So it's A, and A meets this matrix. And again, it's good for you to know, like, there's a formula for multiplying matrices with the summations and so on. But there's a formula in which you can tell what happens if a matrix hits a column and so on. So here, the result will be a matrix, also a tall matrix, where the first column will be AC1, and you'll have the columns ACK. I mean, surprise, surprise. A times C1, A times C2, and so on. But now, what happens? So, each of these columns, where do they live? So, AC1, ACK live in U because U is A invariant. And now, if you live in U, who tells you how everything looks like in U? A basis. And we have a basis, C1, Ck. So each of them is going to be written as a linear combination of so let's just, I'll just do one example and then I'll write down so AC1 is going to be maybe alpha 1 C1 plus alpha K Ck. Okay? But how can you write this as a product of two matrices? You can write it as maybe this matrix C1 Ck, and you multiply it by alpha 1 alpha K, something like this. You see, think about C1 Ck as kind of like numbers, the way you do dot product, and you're going to be C1 Ck meets alpha 1 alpha K. Okay? So, well, what's going to happen? This happens for AC1. So AC1, you can write it as this matrix R times a vector. Well, it's going to happen for AC2. It's going to happen for everything, ACK. So these vectors, alpha 1, alpha K, you put them together in a matrix. And what you will get is, let me write it here. So from here, again, because so we're using both things because U is A invariant and C1 Ck is a basis of U, we get that. So let me do it kind of on the picture. A, which is a big matrix n by n, meets this tall matrix n, which is R by K. And now you see, like for each column C, I get a vector here, and I can put those vectors together, and I'm going to get something here of those vectors. Let me see how I call it. But no, I got it the other way around. Will be this tall matrix again, the R, which is n by k, times something small here, which is k by k, and I call this b. So I wanted to show you this because tomorrow we're going to talk about equitable partitions and interlacing and so on, and we'll see this picture again about A-invariant subspaces and so on. And it's useful to kind of, it takes a little bit to get used to it, but it's not super complicated once you write it down and you think about it yourself. So is this clear? So we get that AR equals RB for some B matrix, which is MKR. So like I showed you here how AC1 is going to be C1 CK times alpha 1 alpha K. If you do AC2, it's going to be maybe beta 1 C1 plus beta K CK, which is again the same matrix of which is R times beta 1 beta K. So you just put these vectors of coefficients, you put them together and you get that. Okay? Okay. Okay. So, I mean, now kind of I tell you about some things, it's easy to lose track of what we're trying to prove. We're trying to prove that U contains an eigenvector of, okay? So an eigenvector in U is going to be some linear combination of this C1, CK. So somehow we have to make an eigenvector of this form. Like a C times something, we have to make an eigenvector, okay? This is good. Okay. Now, what else can we say about this matrix R? Because the columns are orthonormal, then which way? Which one? So, from the definition of R, R transpose R. R transpose R equals IK. There you go. Okay. So now, again, it's useful for problems. You see this, you're looking at the conclusion. What do I want? I want an eigenvector for A. I want A times something on this side. Now on this side I have R, which works in my favor because I want an eigenvector that looks like this, which is exactly R times something. Okay, I already have A and R. I'm looking for some kind of coefficients that will work. Well, then let's look on the right hand side. What do I have? I have R, I have B. What do I like about B? B is square. So because it's square and it's real, it has an eigenvalue and an eigenvector. So let's try to use that and see if it works, okay? So let me erase here. So because B is in here, there is let's say theta in R and let's say V in RK, V not 0, such that B times V equals theta times V. So B is square matrix and it's real, so by the stuff I bored you at the beginning of the lecture, there is a real eigenvalue, real eigenvector, so that happens. And now I have ARB, RBV, so we just take this equation and you multiply both sides by V to the right and see what happens. So from AR equals RB, we get that ARV equals RBV, and now the BV gets replaced by theta V, and this is going to be theta times RV. So now you can be, yeah. So ARV became theta times RV. So the same trick question as before. Can I say that you have to check if it's non-zero? Well, somebody's going to help me. Is it 0 or non-zero? RV, you have it here. You see, like, anytime you multiply the matrix R by a scalar, what do you get? You get a linear combination of the columns. And what were the columns? They were orthonormal, so linearly independent. So you can say because the columns of R are linearly independent, RV is not the zero vector. So I have A times RV equals theta times RV. I have RV is not zero. Do I have to do anything? Well, RV is what? Is a linear combination of the C1, so it's going to be in U. So this implies that RV is an eigenvector of A that is contained in U. Okay, so I think we proved that. Okay. Okay, I lost track. You look through your notes. We had the sequence of steps. This was the one that I just erased. Was step 3. Okay, so obviously. Can I erase on the left side? It's okay? Okay. So, okay, step 4. Okay, let K be natural number, K between 1 and n minus 1. What we'll show is that any set U1 UK of orthonormal eigenvectors of A can be extended to a set U1 UK plus 1 of orthonormal So before we go through the proof, let's just see that this step is going to finish the spectral decomposition, because if I'm able to prove this, then I will be able to argue that the space Rn has a basis of orthonormal eigenvectors, because at the beginning we argued that real and symmetric matrix will have one eigenvalue, one eigenvector. Okay, so you normalize that eigenvector so that it has length 1. It's an orthonormal system, and then you start with that and you apply this step. So you take that eigenvector, you can extend it to, you can add another eigenvector to it that is, you know, in the complement of it, in the orthogonal complement of it, and you keep doing this until you cannot do it anymore, until you get n, and you're going to have a basis of orthonormal eigenvectors. But this step also, you see, it's general, but it gives you an idea about what to do and where to look for. So you have kind of from the statement, you can get an idea about what you're going to do. So you have U1, UK, already some orthonormal eigenvectors. And now what we're saying is that you can add one more eigenvector to it, that this is orthonormal. Like this one having length 1, it's easy. Once you find it, you normalize, that's not a problem. But because of the statement, you know where to look for UK plus 1. If you have U1 UK and you're searching for something that's orthonormal, you want to look for UK plus 1 in the orthogonal complement of the space spanned by this. And that's essentially the idea of the proof. So let's what did I call it? U, W. Okay, let's call it W. Let W be the span of U1 UK. Okay. Now, what's so special about W? Because these are eigenvectors, think about what we've done so far. What can I argue about W? What kind of a subspace it is? Invariant, because U1 UK are eigenvectors. I forget, this is obviously from the definition. W is an A invariant subspace. A invariant subspace, that's it, of Rn. Okay, so now this is step 4. Which one of the steps 1, 2, 3? It's one that I left you as an exercise. One of the ones I left you as an exercise. If you have an invariant subspace, what else is an invariant? Yeah. Which one was that? 2. By 2, W perp is also and now, if you have an invariant, what are you guaranteed to find in there? An eigenvector. This is from step 3. By 3, so you pick an eigenvector there, you make it length 1, and because it's in W perp, it's guaranteed to be perpendicular here, and you're done. Make sense? So yeah, don't be shy about asking questions, yeah. I'm sorry if you know all this stuff, but I figure it's good to kind of start. And the thing, again, like the stuff that I showed you about this U invariant subspace, we'll see it again tomorrow when we talk about quotient matrices and equitable partitions and so on. Okay? All right. So I'm not gonna, okay, you can write the conclusion. So from 4 implies that there is an orthonormal basis of Rn formed by eigenvectors of A. Okay. Now, jumping a little bit ahead, because I haven't talked about graphs and adjacency matrices and so on, but I can still give you an exercise. Where are we? Exercise 4? 4? 4. Okay. I assume, consider the adjacency matrix of the complete graph. Kn. Find an orthonormal basis of Rn formed by eigenvectors of A. So just, you know, I'm jumping a little bit ahead, but the complete graph Kn, you have all n vertices joined by any two vertices, distinct vertices joined by an edge. So here this is K5. And the adjacency matrix of Kn is going to be, you have 0 everywhere and you have 1, or the same thing as all 1 matrix minus identity. Okay, so just something for you to do. Okay. So now, the remaining half an hour, let me give you a different perspective on this thing. So what I show you now, this kind of self-contained proof that every real and symmetric matrices has a real and symmetric matrix you can get a basis of eigenvectors that span the whole space, and we will apply this from now on. But I want to show you a different perspective, and it's using which is broader, and it allows you to handle all the spectral decomposition theorems, Hermitian and normal and so on. Now, so in this book by Horn and Johnson, if you go in section 2.3, you will find the following quote. Perhaps the most fundamentally useful fact of elementary matrix theory is a theorem attributed to Schur. Okay, then they go on to state. Now, this Schur theorem, I mean, there are many Schur theorems in mathematics, but this one about, let's say, Schur upper triangular theorem. In words, it says the following. Any square complex matrix is unitarily similar to an upper triangular matrix. So if you put no restriction on your matrix and you take any complex matrix, so I will write it down here what I mean by this. So for any A complex matrix, where did I write it? There exists U and T such that, so here it's over complex, so the transpose gets replaced by this conjugate equals T, and so U is unitary, so U star U is identity. You can say, okay, U star U, so this means U unitary, and T is upper triangular. So T is square, here you have 0. Okay, so you can have here T, you can have here T11, T and N. Below them you can have, I'll put star, you can have whatever you like, but above the main diagonal you have 0. Okay, so this is general. Yeah, question? Huh? Oh, the other way around. Sorry, yeah, I got myself mixed up. You're right. Yeah, you're right. Upper triangular is the other way around. My bad. So above the diagonal you have everything and below it. Thank you. Very good. So if you have no condition on your matrix, any matrix, the best you can do is it behaves like an upper triangular matrix, or of course lower, the one that I wrote before, lower triangular matrix. Now this Schur theorem, again, it's a general statement, and let me write it here. So it's going to imply the spectral decomposition theorem for normal matrices spectral decomposition theorem for Hermitian matrices and from which you get the spectral decomposition theorem. Okay, so this one we already saw it, like we saw the self-contained proof. But this spectral, this general theorem, it can give you something for complex matrices. So Hermitian matrices, A complex such that A equals the complex conjugate, and normal such that A. Now here, if this one gets replaced by A is real, then you replace the star by transpose. Okay. So you've probably done this in linear algebra. I don't know how, what books you used or that. But again, this theorem implies these theorems. Now, what's the statement for each of them? So the statement here is if you have a normal matrix, then A is unitarily similar to a diagonal matrix, and diagonal matrix will have the eigenvalues which are complex for normal. Now for Hermitian, A is unitarily similar to a matrix, and again on the diagonal, on the diagonal you'll see the eigenvalues, and this will be real. There will be real here, and there will be real here. Okay, so here it will be unitarily gets replaced by this real and orthogonal matrix, which is the one by eigenvectors. Okay, so again, I think it's useful for you to know this, to have this broader picture, because when you, again, if you come to encounter papers, like I said, especially now, there's some push about doing something for directed graphs. And there are several papers which study directed graphs, and the approach is having like a 0-1 matrix for these directed graphs, it's tricky to find a symmetric matrix, so people look for Hermitian matrices. to do something. I know of one paper that is try to do the spectral theory for directed graphs using normal matrices. But normal matrices, because you have this condition, this imposes like may not work for all the directed graphs and so on that you use. Here, this one seemed to be the simplest that you can. And like I said, I may mention a little bit something towards the end of the course, but for now, I wanted for you to be aware of this. Now, okay. So this is you know, this and this they're not hard, but they're not trivial. So you may think that this here, it's some it is a super theorem because it implies all of them, but it's actually not that complicated. So I'll give you a sketch of this and then we finish for the morning, okay? Let me erase here. So I'll just copy the statement from here, from the bottom. So for any A, let's say such that okay. Okay, so the whole thing is here, you give me the A, you're looking for the U, you're looking for the T, okay? Now, in the previous parts, what was U formed by? Like in the case of spectral decomposition for theorem, like how can you think of U? The columns are eigenvectors. So that's the same idea here. So what you start is, because A is a complex, A has a let's say lambda 1 complex and V, okay, such that so you can take V to be of length 1. Okay? And now what you're looking for? You're looking for U unitary, okay? So what we do is, let's attempt our first try at U. What we'll do is take U1, a matrix where you put V in the first column, and then you don't know what to fill it up with, because you don't know if you'll have eigenvectors and so on, but you know for sure that you can do Gram-Schmidt, and you can fill it up with some vectors U2, Un, such that U1 star U1 is identical. So you get you get to start with one vector V1, which you know that every complex matrix is going to have one eigenvalue, one eigenvector. Okay, so you start with that. And then you see, like, you can rewrite this as AU equals U transpose. So the first calculation you'll do is here, A times U. The ones that from, I don't know, experience and so on, you want to pick, eigenvectors are going to be your best choice here. And you don't get the full, you may not get the full set of eigenvectors, but you have one. So okay, you use that. Take one eigenvector, and what are you going to fill it up with? Fill it up with whatever you can. You can fill it up so that this is unitary, okay? And then you say, okay, what is going to be U1 star A U1? So it's U1 star, and now A U1, it's going to be here, it's going to be lambda 1 V, lambda 1 U2, lambda 1 UN. That's when AU1 becomes this. Because when A meets V, it becomes lambda 1V. This one's, yeah, here I'm wrong. Yeah, this is A, sorry. Yeah, I was got carried away. Okay, and now what comes from the left? From the left is U1 star, which is V1 star, U2 star, okay, and lambda 1, I call it V. So the main thing is we want to see what happens here on the first column. Lambda 1 on the first value. What's the value here? 0. Yeah. So you see, just the simple fact that you took this as an orthonormal basis, it clears out your first column, okay? And then you're going to get something here, and you're going to get something here. I don't know, let's call it A2. Okay? So now, now you kind of see the idea. What's the idea? You want to get to upper triangular. You already cleared up the first column. You want to go inside here, and you want to clear up the same thing. So you do the same thing. A2 is a complex matrix. You pick an eigenvector, fill it up with a unitary. Now, you still have to do this calculation for the big matrix. A2 is n minus 1 by n minus 1. So you just put a 1 in front. You kind of border them with a 1 on top. And you do the same calculation, and you see that this procedure will allow you to clear up the whole thing here. Okay? So it's essentially, what is it? It's Gram-Schmidt. Like and the fact that you have one eigenvector to start with. Like you need that eigenvector to get you here, to get you this value on this position. Okay? And now this is how you get an upper triangular. Now this theorem, as you see, because your matrix is complex, you get upper triangular. But then when you put these conditions on your matrix to be normal, Hermitian and so on, that's going to force this upper triangular to be the same as them, to be normal, Hermitian, real, and symmetric, and that's going to force the upper triangular matrix to be a diagonal matrix, and that's gonna do it. Make sense? Yeah. Questions? No. Okay. Yeah.
Diagonal matrix. For matrix A.
Can you speak louder? I can't hear.
If for a matrix A, there exists some unitary matrix of the Q star A is equal to diagonal matrix.
Then you don't need anything else. You are like, that's kind of the place. That is, in some sense, that's the happiest situation that you can be, because that's the same thing as having like this orthonormal basis.
I'm saying that
Yeah.
does it imply that it's a normal or?
Yeah. You can do this calculation. Yeah, like if you so you're saying if A is unitarily similar to a diagonal matrix, then okay, exercise what number? 5. Exercise 5. There you go. You answer your questions already. So don't be scared. Just because you ask a question doesn't mean you get an extra exercise, but sometimes it can happen. So okay. Okay. Now, one more quick thing. So in the book by Horn and Johnson, they don't have this diagram, but they have a bunch of consequences of this. And like I said, this is it's a really, really useful theorem, and it has many consequences, not just this. It has a consequence that you may, sometimes when you're a student, you may struggle to remember Cayley-Hamilton theorem. You know, you can remember Cayley-Hamilton theorem. You have characteristic polynomial, you plug in the adjacency matrix, you're going to get the zero matrix. And it's easy to remember the wrong proof of Cayley-Hamilton theorem. Which one is that? You take characteristic polynomial and you replace the x by a. And so therefore determinant is zero, so you're done. So that's the wrong proof. But the sure upper triangular theorem, what it does, it allows you when you're dealing with your matrix, you can replace it by upper triangular. And for upper triangular theorem, this Cayley-Hamilton theorem is it works. It is still some work. I'm not going to do it here, and we're not going to do it in the exercises. But it's another. And there are many other consequences that that are in the book, but I'm not going to do here. But for us, these are like the important ones, and especially this one that we've already done. Okay, so I thought I'd mention it. I got this. Okay, I'm supposed to talk about Perron-Frobenius. Now, let's talk about that quickly. I have 10-15 minutes, so let's talk about Perron-Frobenius. Can I erase here? So now we can go into talk about graphs and all that. So here's a notation that I'll use for graphs. So graphs and matrices. So I'll have gamma VE. That's the notation that I will use for. So again, this will be undirected graph. And now to a graph, you can associate infinitely many matrices. You can define all kinds of matrices. The most popular ones are going to be the adjacency matrix. So this will be A of gamma. And let's do it by an example. So let's say this is my graph, vertices 1, 2, 3, 4. Okay, just a silly graph. And the adjacency matrix, so the rows and columns of A are labeled by V, by the vertex set. And then in the position xy, we write down the number of edges between x and y. And this is kind of the general for multigraphs or loops and so on. Since I'm not going to talk about that, at least for the first few days. So if the graph is simple, so a graph is simple if you don't have multiple edges or loops or anything like that, then here you can just say AXY is going to be 1 if x is adjacent to y and 0 otherwise. So from this graph, the adjacency matrix 1, 2, 3, 4, 1, 2, 3, 4, 0, 0, 0, 0, and then I have edge everywhere except 1, 1, 1, 1, 1, 1, 0, 0, 1. Okay, yeah. Now the second matrix that people study, so this is the adjacency matrix. So the Laplacian matrix It's usually denoted by L or L of gamma. And for now, I'll just give you the entry-wise definition. So again, the rows and columns are labeled by V. And if you have L of xy, now you're going to have three things. It's going to be the degree of x if x equals y. So I'll tell you in a second what the degree is. It's going to be -1 if x is adjacent to y, and it's going to be 0 otherwise. So the degree of x this is the number of edges, the number of neighbors of x. So here, if you want to do L, the same thing, 1, 2, 3, 4. So this one has degree 3, 1 because it has 3, and then 2 has degree 2, 3 has degree 3, and this one has degree 2, and then you have -1, -1, -1, minus 0, 0. So these are the main matrices that we'll study in this class: adjacency matrix and Laplacian. There are many other matrices, like I said. There's signless Laplacian, normalized Laplacian. Distance matrix will come up in some play a little bit later, but this will be the main matrices we'll study. Okay, so I think I'll leave Perron-Frobenius for well. Maybe I'll state it, and then we can discuss it after the break. Okay. So again, because we're looking at undirected, that's all these matrices that we'll have will be real and symmetric, and you get this kind of useful fact that you have a basis of orthonormals immediately, and that's going to drive most of the things that we'll do with eigenvalues and eigenvectors. Now, here's one thing we're going to do after the break. So this will be, so there is something called Perron-Frobenius theorem. So I'll give you the light version for undirected graphs. Light version. This implies that there is a more general version. There is a general version for something called irreducible matrices, but we'll do this for undirected graphs. And he says the following: let gamma be a connected graph. Now, we'll talk about the eigenvalues of the adjacency matrix. So denote, this will be the notation we'll use by λ1 greater or equal to λ2 greater or equal to λn, the eigenvalues of A. So here you see I put greater or equal, so you could have repeats, but in total I have n eigenvalues because I have n orthonormal eigenvectors. So that's my notation. λ1 is the largest. Then 1. So this is a connected graph, so again we assume we have at least one edge and so on. So then λ1 is positive actually. λ1 is going to be strictly greater than the absolute value of lambda j for any j from 2 to n. So this λ1 it's a positive and it's the largest. It's largest, but it's also, you could say, well, here maybe I get something negative, and that something negative is very negative. Well, it cannot be very negative because it's. What is it? What's a? Yeah, that's a very good that's a very good. So maybe you have a very good point. So let me put it this way: lambda 1 bigger than, greater or equal than absolute value of lambda n. You're very good. Yeah. And 2. Yeah, I got it. Lambda 1 bigger than lambda 2. That's what I wanted to say. Lambda 1 is bigger than lambda 2. And then 3, you can find the multiplicity of lambda 1 is 1, and its eigenspace is spanned by an eigenvector with positive entries. Okay, yeah, so in absolute value it's greater or equal than, so lambda 1 is positive, is greater or equal than absolute value lambda n. Thank you about the bipartite. Lambda 1, here you have actually strict inequality. It's always going to be the winner, only one winner. And then the dimension, because of that, lambda 1 is strictly bigger than lambda 2. The multiplicity is 1. So that's the same thing as lambda 1 bigger than lambda 2. And the eigenspace, you can find an eigenvector whose entries are all positive. Obviously, you can multiply by -1, you get all the entries negative as well, but positive, it's better to be positive than negative. Okay, so yeah. So I'll stop here and then we do this after the break. Thank you.